My name is Martin Molan. I'm a PhD researcher at University of Bologna and a researcher on Graph-Massivizer project. Today, I want to talk to you about the Graph-Massivizer approach towards a European sustainable data center digital twin. This work has been done by my colleagues from University of Bologna, Junaid Ahmed Khan and Andrea Bertolini, my colleagues from Cineca Supercomputing Center, Roberto Atura and Giorgio Pedrasi, and other colleagues and collaborators from the Graph-Massivizer project. Graph-Massivizer is a Horizon Europe-funded project for high-performance and sustainable processing of massive graphs. By massive graphs, we mean graphs that have dynamically changing topologies and consists of billions of vertices and trillions of edges. Of course, we are not trying to just create a platform that supports the processing of massive graphs. We also want to do that in a socially responsible way with regards to energy efficiency and the total cost of ownership. In this presentation, I will first present the ambition of the Graph-Massivizer project and then showcase one of the use cases where we can use this technology. As I've said, the first section of the presentation will present the Graph-Massivizer platform and its different elements. Then I will showcase why this is useful on the case of understanding and monitoring the Marconi 100 supercomputer with anomaly anticipation use case. I will conclude my presentation with scientific conclusions and the impacts of the proposed technologies. Okay, so what is Graph-Massivizer? The objective of the project is extremely ambitious. What we want to do is to create a platform that will allow the processing of massive graphs. We want to be able to do that from the birth of the graph all the way through the whole life cycle of the massive graphs. This means that we have to cover the creation of the graphs from the raw data with the graph inceptor, processing of the graph with Graph-Scrutinizer, optimization of this processing by Graph-Optimizer and Graph-Greenifier, and then deployment of this processing to the best possible hardware or resources with Graph Choreographer. The role of Graph Inceptor, which is the first part of the platform, is to transform the raw data, be it from monitoring system or from existing databases, into a graph form. Then this data is passed to Graph-Scrutinizer. This is where all the data or graph processing lives, from the traditional graph processing applications such as community discovery to machine learning applications like graph neural networks used in this paper. Then but of course, we don't want to just process the data. We want to do that in an optimal way. This is the role of Graph-Optimizer. Graph-Optimizer attempts to optimize this data processing with regards to computational efficiency. But computational efficiency is not the only metric of optimization. As said in the beginning, we also want to do that in a socially responsible way. This is the role of Graph-Greenifier. We want to optimize the processing of the graphs with regards to energy efficiency and actual energy sources that we are using for this processing. The outputs of the Graph-Optimizer and Graph-Greenifier are then fed to the Graph Choreographer. Based on this information, the Graph Choreographer sends the graph processing workload to the optimal platform or hardware to do it. Essentially, the role of Graph Choreographer is to take the state-of-the-art of serverless processing paradigm and rethinking from the perspective and prism of graph processing workloads. Okay, so now that we briefly, or at least generally understand what we are attempting to do with Graph-Massivizer, let's delve into one of the use cases. This is the creation of digital twin, graph digital twin of Marconi 100 supercomputer, and specifically the anomaly anticipation model for Marconi 100. Of course, we all know that supercomputers are becoming an exceedingly important piece of technology in our society. But at the same time, they're becoming increasingly more complex. The current pre-exascale and exascale system already consists of thousands of compute nodes. At this scale, it's impossible for the system administrators to process them alone. This is why we have to introduce certain machine learning methodologies in order to support them. But of course, before we create any sort of machine learning application, we first need the data. The data is collected from raw sensors, from hardware sensors located at actual compute nodes, and the software monitoring system installed on the compute nodes with Examon monitoring platform. Examon monitoring platform is a technology developed by University of Bologna to monitor the several generations of supercomputing system. Within Graph-Massivizer project, we aim at upgrading the Examon platform by taking the raw data as collected by it and transforming it into a graph representation with graph inceptor. Specifically, we take the raw data from Examon, combine it with an ontology, which is a knowledge graph mapping all the possible connections between the metrics, and then transform it into a graph representation. Okay, so what do we actually do then with this graph representation? As I've said before, our main goal is to support the role of system administrators in supercomputers. So what is the first task that we do? We want to make the supercomputer as reliable and as available to the end users as possible. This is why the first thing we do in introduction of machine learning methodologies to operational data analytics in supercomputer is anomaly prediction. We want to understand which nodes are likely to fail so that we can do something about it, so that we can be proactive in our maintenance. We try to understand and try to prevent the nodes that are likely to fail, or at the very least, we try to avoid scheduling important and complex and costly compute jobs on the nodes that are likely to fail. So the longer the period of anomaly anticipation, the more proactive we can be with the handling of anomalies, and the more time we have to react to them. So here I'm just presenting the preliminary results of what we have done. We have constructed a convolutional graph neural network based on the topological information from the compute nodes. And the information that we have shows that we are already in anomaly anticipation, achieving results that are comparable to state-of-the-art anomaly detection models. Now, and this is remarkable because anomaly detection should be a significantly easier problem than anomaly anticipation or anomaly prediction. So why are we able to do that? The state-of-the-art for anomaly detection are per-node models, specifically the model RUAT, which is trained in an unsupervised way, but for each node specifically. So why are we able to outperform RUAT, to not just detect, but to anticipate failures? We have more information than that models, because instead of creating a per-node model, we can create a model for the whole compute rack, leveraging additional information about the spatial proximity of the nodes in the compute rack. We are leveraging this additional topological information. And this is the strength of the graph processing, because essentially graph processing allows us to take not just our raw data, but also all the additional information that we have about this data to make more effective and more powerful models. We are able, with anomaly anticipation models, we are able to achieve non-trivial models with prediction windows that are as long as 48 or even 72 hours in advance, which of course gives system administrators plenty of time to react to these problems. Okay, why is this important? Of course, making supercomputers more reliable and more available is a significant benefit, not just in a commercial sense. European Commission invested over 8 billion in HPC alone, but also in a societal sense. If you remember from the times of COVID, supercomputers were one of our most important weapons in fighting it. So of course, making them more reliable makes a lot of sense. But we are not aiming to stop here. These results on Marconi 100 are just preliminary work. Now we want to transition to Leonardo, which is a pre-exascale computer. What I wanted to do in this presentation is to showcase first what we are trying to accomplish, what is the Graph-Massivizer platform, and then to motivate you to show that graphs are an extremely powerful tool that leverage this additional information and leverage the data that we are already producing. Of course, the use case presented here is just one out of many use cases that we are exploring in this project. But this is the one where we already have some preliminary results and preliminary data. Other use cases that will all take advantage of the platform that we are developing include global event predictions, financial data analysis and generation, and smart manufacturing analysis. So there is a lot of exciting stuff happening in this field. And of course, what we're presenting here is the first use of large, not yet massive, but at least large graph for operational data analytics and processing of supercomputing data. I would advise you to, thank you for your attention. I would advise you to visit our websites. There we will publish all the additional information, scientific research, and all the resources we create in developing our project. And of course, through that website, you will also be able to contact either me or any of my colleagues on the project. Thank you.